Let's just take a minute and go over an example of interpreting the slope in the y-intercept for the least squares regression line. The equation of the regression line for predicting the price of a car based on the number of miles driven is shown below. So here's your equation. Now notice that hat is predicted. The predicted price is equal to 38,257 minus 0.162729 miles driven. Now, what I want you to notice here, we'll go over this later, is whenever you're dealing with your least squares regression line, you must define y and you must define x. So you have two choices of writing this equation. You can either write y hat equals and then miles driven as x, but then you would have to define y hat equals the predicted price and x equals the miles driven. Or you can just put the words right into the equation. So the predicted price is equal to, and then instead of x, you're putting miles driven. That's what I suggest doing so that when you're filling in data points, you know exactly where to put it for price or miles driven. Let's identify the slope and the y-intercept of the regression line and interpret each value in context. Remember, your slope right here is the number in front of x, or our miles driven. So what does that tell us? That tells us that the price of a used Ford F-150 is predicted to go down by $0.1629 or $16.29 for each additional mile the truck has driven. If you're having trouble writing this equation, here's what I always do. I always write the slope. I put it over 1, okay, just to make it a fraction, and then I write on the bottom and the top what they mean. So 1, the bottom is your x's. In this case, that's miles driven. The top is your y, that is your price in dollars. So then I make a sentence out of this. So I just kind of like work this way and I say, for every 1 mile that's driven, the price goes down, since it's a negative, by $0.1629 or $16.29. Okay, so that's just the way that I do it. The y-intercept in this case is 38,257. That is, notice, the predicted price of a Ford F-150 that's driven 0 miles. And if you're ever not sure how to do this, just write it as an ordered pair, 0, 38,257. And when you do that, you know that this 0 is your miles driven. So for every 0 miles driven, the predicted price goes up to, or starts at, 38,257. Okay, so just make sure that you use the word predicted. The word predicted and in context are your key here. Now, we kind of already talked about this. There's 2 ways to write your least squares regression line. No matter what way you do it, you have to define the variable. Notice here, this one is in context already. The variables are defined in the equation. There's a hat on the response variable y, and x is just written as your miles driven. The other way to do it is just to write y hat equals your equation, put your x in there, but then you have to define x and y down here. Notice when you define y hat, it is the predicted price, not just the price, and x is your miles driven. So just make sure you decide, whatever you decide is totally fine. Just pick one and make sure your variables are defined and you're using the word predicted. So let's take a look at our equation for our Ford F-150. Now, notice the slope is negative 0.1629. It's a small number, okay? Now, so the slope is a small number, but it does not mean that the change in miles has little effect on price. So all it means is for every miles that I'm driven, the price goes down by a little bit. So it doesn't necessarily mean that it's the miles driven does not have a huge impact on the price of the car. The slope helps you to make the predictions, but it does not tell you how strong a relationship exists. Do you remember what that is? Remember, R is the only thing that tells us the strength of the linear relationship, okay? We also need to be careful with y-intercepts. Sometimes they don't always make sense. In this case, the y-intercept is 38,257. In this case, it actually does make sense. If the truck has driven 0 miles, then the predicted price is 38,257. Okay, so sometimes you'll get y-intercepts that don't make sense. So just make sure that when you're interpreting them, you kind of take a look at them and understand that they won't make sense, especially if the scatter plot does not have an x value close to 0. All right, so how can we make good predictions? So we can use a regression line to predict the response variable y for a specific variable of x. So use the regression line to predict a price of a Ford F-150 with 100,000 miles. So now that we have our equation written out, that's easy to do because I can just go ahead and plug in the 100,000 in for the miles driven. Now notice the hat once again right here. It's the predicted price of the car. We don't know what the exact price is because I don't have an exact data point. It's the predicted price of your car. Okay, let's take a look at the next example. Use the regression line to predict the price for a Ford F-150 with 300,000 miles driven. So once again, we're just going to insert the 300,000 for the miles driven, use our calculator, and say, hey, wait a second. If we drive it for 300,000 miles, the predicted price is negative $10,000. That literally means you're paying somebody to take your car. That's a little bit crazy. So what's wrong with that number? It's not realistic at all. Here's why. If we take a look at this data only is going up to about 160,000 miles. It actually looks like it ends at about 150,000 miles. This data point of 300,000 is like way over here. It is way outside of the range of the data that we have gathered. That's called extrapolation. So when we extrapolate beyond the x values that we have collected, it does not necessarily give us a good representation of the predicted y value. So just make sure that you're aware of that when you're making predictions. Most of the predictions that are accurate are going to be within the x values that we have collected. Maybe a little bit outside, 1 or 2, but not a significant amount. We just talked about the fact that that's called extrapolation. So we can use a regression line to predict the response variable y based on the explanatory variable. The accuracy of the prediction depends how much of the data is on the line. You can substitute any value of x into the equation and make a predicted y value like we did on the previous slide, but it doesn't always make sense. So you have to be aware of extrapolation. It's the use of the regression line for prediction values that are outside the interval of the explanatory variables or your x values, okay? So such predictions are not accurate. Don't make predictions of values of y that are much larger or much smaller than the data that you have collected. This is why the meaning of the y-intercept, or whenever x is equal to 0, is not always accurate or meaningful, because often at x equals 0, we don't have data that was collected, therefore it's extrapolation. Let's take a look at an example. Some data were collected on the weight of a male white laboratory rat for the first 25 weeks after its birth. A scatter plot of the weight in grams and time since birth in weeks shows a fairly strong positive linear relationship, and the regression equation, weight is equal to 100 plus 40 times the time, models the data fairly well. Take a minute, write this, what is the slope of the regression line, interpret it. Go ahead and try that. As you're working through these, hit pause and then go ahead and check the answer. The slope is 40, so that's telling us for each additional week, we predict that the rat will gain 40 grams of weight. So just be careful with that. Make sure you're using your prediction. What is the y-intercept? Go ahead and predict that. The y-intercept in this case is 100. So the predicted weight for a newborn rat, so you're coming from the ordered pair 0, 100, okay, is 100 grams. Let's predict the rat's weight after 16 weeks. go ahead and plug in 16 into the time. The predicted weight is 740 grams. Now, notice it collected data for the first 25 weeks, so this 16 weeks is not extrapolated. It is within the range of X values that we've collected. So should we use this line to predict the rat's weight after 2 years? Use the equation to make a prediction and think about the reasonableness of this result. All right, so what did you do? The time measured is in weeks, so make sure that you have 2 years becomes 104 weeks, or 52 times 2. Then when you put that in, you get 4,260 grams, which is 9.4 pounds. That is a big rat. That is huge. It's like a city rat, okay? That's about the weight of a large newborn human. So this is totally unreasonable because of extrapolation. Next thing we're going to discuss is residuals. So in most cases, the line is not going to pass through every single solitary one of the points that you collected for your scatter plot. We already talked about that a good regression line makes the vertical distances from the line as small as possible. So what exactly is a residual? So a residual is the difference between the observed value of the response variable and the value predicted by the regression line. So basically what that means is here's your data point, here's the predicted value. So this is going to have an xy, this is xy hat. The residual, okay, the residual is basically what is the vertical distance of this line. So in order to get your residual, okay, all you're going to do is going to be, it's the observed value of y minus your predicted value of y, or basically y minus y hat. Okay, so you'd have to know the y value from your data point, but also keep in mind, if you weren't given the predicted value, you could plug that x into your equation and find out what that y hat is. So basically, what is your vertical distance between the two? So it's your observed y minus your predicted y, or y minus y hat. So let's just take a look at an example of how we can find a residual. It says find the residual for the Ford F-150 that had 70,583 miles driven at a price of $21,994. Now, that is actually an ordered pair. This is your x, this is your y. That's your observed value. I actually went out and I gathered that. The residual is, we want to find this vertical distance, okay? So if you think about it right here, what's this vertical distance? So this y value was 21,994. Okay, what is this predicted y value? So I have to figure out what the predicted y value here is. So now I can fill in my observed value of y pretty easily because it was given to me. How do I find that predicted y? Well, the predicted y comes from your equation. So we have the regression equation right here. Y hat equals 38,257 minus 0.1629x. We can take that 70, because the x value is the same here. We can take that 70,000 and plug it in for x and find the predicted y. So when I plug that in, I get the predicted y is 26,759. So your predicted y is 26,759. So I want the difference between the two. So what was our observed y? That's what we were given from the beginning, minus the predicted y that we found out right here. And the residual is negative 4,765. So what does that tell us? Negative residual means that the observed value is below the line. Since the observed value is below the line, that means the line actually overpredicts the cost of the car. Okay, so let's interpret the residual. So that's negative 4,765. So basically what that means is, if this is the observed minus the predicted, okay, the actual price of this truck, so here's your what you actually collected, is $4,765 lower than, because this is a negative, the expected price based on its mileage. The actual price might be lower than the predicted as a result of other factors. The truck might have been in an accident or might need a new paint job. So to interpret the residual, take a look at the residual and determine if the observed value is higher or lower than the expected value. Put your answer in context.